All right, let's continue.
Cool. Next question. How do some insects survive being frozen and dried out at the same time? Basically turning into tiny biological raisins that come back to life with water.
When you say raisin, do you mean that they dehydrate and get deformed like raisins, or do they stay pretty much the same form?
Sorry, I'm having issues right now. Our systems are experiencing heavy load. Please try again later.
Do they get deformed like a raisin does when they dry out, or remain undeformed?
They actually do shrivel up. Some of them look like little crumpled husks, but here's the wild part. They bounce back when rehydrated, often without permanent damage. Take tardigrades or certain beetle larvae, they enter a state called anhydrobiosis. They lose almost all their water, like down to 1 or 2%, and basically shut down their metabolism. Their proteins and membranes are protected by special molecules, like trehalose and LEA proteins, that act like cellular padding during the drying process. So, yes, they deform, but they've evolved to tolerate that deformation. Their molecular structures stay intact, even if their bodies look like tiny raisins until you add water. Then, back to normal like nothing happened.
Is the padding at the molecular level?
Yeah, exactly. It's molecular level padding. Trehalose, for example, is a sugar that replaces water around proteins and membranes. Water normally helps keep proteins folded and membranes flexible. When it's gone, things can collapse or stick together. Trehalose steps in and forms a kind of glass like matrix that holds everything in place, preserving the shape and spacing. Then you've got LEA proteins. They stay disordered in water, but as the cell dries out, they fold into protective structures that coat and stabilize other molecules. They're like little molecular bubble wrap. So, yeah, these organisms use biochemical tricks to keep their cells from falling apart, even when they look physically shriveled. The real preservation is happening at the nanoscale.
When scientists were working out how to freeze embryos, were they being inspired by these natural examples, or just basically guessing chemicals?
At first, it was mostly guessing and testing. Early cryopreservation researchers in the 1940s and 50s didn't know much about what nature was doing. They were experimenting with chemicals like glycerol and DMSO simply because they noticed they helped sperm or cells survive freezing better than water alone. But as the field matured, scientists did start looking to nature for clues. They studied frogs that survive freezing, insects that undergo anhydrobiosis, and fish that produce antifreeze proteins. That natural resilience started informing new strategies, like using sugars such as trehalose inspired by dry tolerant organisms, or designing synthetic ice blockers based on antifreeze proteins. So the inspiration shifted over time, from trial and error to biomimicry. Nature had already solved some of these problems over millions of years. Scientists just had to figure out how to translate them into something that works in the lab.
How did they originally find those chemicals just by chance? I mean, what was the circumstance that by chance made them find them?
It's a mix of lucky accidents and practical hunches. The first big one was glycerol in the 1940s. A researcher named Christopher Polgy, working in a British lab, was trying to cryopreserve rooster sperm. One day, the story goes, he or a colleague grabbed the wrong bottle, one labeled glycerol, and added it to the sample. Instead of killing the cells, freezing actually preserved them better. That accident kicked off the whole field. From there, researchers started systematically testing similar compounds, like DMSO in the 1950s, because they noticed that certain small water like molecules could get into cells and seemed to lower freezing damage. These weren't random guesses so much as educated stabs. Things that resembled water, could move through membranes, and didn't instantly kill cells. Once they had a few early successes, the whole process got more scientific. Screening compounds, measuring freezing points, looking at cell survival under microscopes. But it all really started with that bottle of glycerol, an unexpected result, and someone who paid attention instead of throwing it out.
Compare glycerol to DSMO at a molecular structure level.
Great, let's break that down. Glycerol is a simple sugar alcohol. It has 3 carbon atoms, each bonded to a hydroxyl group, minus OH. That makes it very hydrophilic. It mixes well with water and forms hydrogen bonds easily. It's kind of bulky and sticky, and it doesn't cross cell membranes super quickly. DMSO, dimethyl sulfoxide, is quite different. It's got a sulfur atom double bonded to an oxygen, a sulfoxide group, with 2 methyl groups, minus CH3 attached. That gives it a small, somewhat greasy character, but still with a strong polar side. Unlike glycerol, DMSO can penetrate membranes really easily. It moves into cells rapidly and drags water with it. So structurally, glycerol, small, sticky polar molecule with 3 OH groups. DMSO, small, polar but hydrophobic hybrid, great at slipping through membranes. Functionally, glycerol is gentler but slower. DMSO is fast and effective, but can be toxic if not handled carefully. They're both cryoprotectants, but they work a bit differently at the molecular level.